KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
KURINJI Education Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
We are going to start wave optics numericals, right? So if we consider optics as one chapter, right? I already told you ray optics is one chapter, one topic from optics, and wave optics is like another topic from optics, right? So anyhow, till now we completed theory from ray optics and then wave optics. After that we started ray optics numericals. So with the previous class we completed ray optics numericals. With this class we are going to start wave optics numericals, right? So it is the first class, that is what wave optics 1 numericals, right? See here, now we are going to discuss exercise problems. Here, see the first problem. Monochromatic light of wavelength 589 nanometers. Monochromatic light of wavelength 589 nanometers is incident from air on a water surface. From air on a water surface. Full stop. What are the wavelength, frequency and speed? He is asking what are the wavelength, frequency and speed of reflected and first reflected and second refracted light, right? So they have given refractive index of water is 1.33, right? So here in two cases, that is what for reflected light you have to find wavelength, frequency and speed, and for refracted light also we have to find wavelength, frequency and speed, right? You know one thing, as I told you in the starting of ray optics, right, while discussing about reflection and refraction, I told you one important point that now I am repeating again. You just keep in mind, light is a form of invisible energy, right? So when light is going to incident at a particular point, basically three things will happen, right? Three things will happen. Here when a light is going to incident at a particular point means when a light is going to move from one medium to another medium. When a light is traveling in one medium, it's okay, because it's an important point, you have to imagine, you have to visualize the situation what I am saying, right? So you just imagine air, because air is surroundings to us, that we are calling it as atmosphere, right? So when a light is passing in air, what happens? Because air molecules are present, these air molecules absorb certain amount of energy. It is the common thing. It is the common thing when certain amount of energy is propagating from one place to another place, right, in a medium. That is the basic observation. That is the basic observation. Okay. But if you see that what is electromagnetic wave picture of light, that is what independent of medium, right? That is what the electromagnetic waves chapter. And as time passes or when the time comes, we'll get that clarity, right? But now what I am saying is, when a light is going to incident at one point on a surface or while entering into another medium, here certain amount of energy will reflect back into the same medium, and certain amount of energy will pass through that medium, and certain amount of energy will absorbed by the medium, right? So here optical medium, for example, a light is going to travel from air to water here. So certain amount of energy is absorbed by the water medium, certain amount of energy will pass through the water medium. So it goes that is what to the bottom of the vessel. Otherwise, if any another medium after water, it will pass through that medium also, right? Based on the situation. Suppose if all the light is absorbed means you can't expect any refracted light. Suppose if the light is going to total internally reflected means you can't see any refracted light after completion of water medium, right? At the same time, certain amount of energy is also sent back into the same medium, that is what air medium, right? So I request you to please keep in mind, when certain amount of light, that is what invisible form of energy, incident at a point on surface of another medium, certain amount of energy will pass through that medium, that is what refraction of light. Certain amount of energy will reflect back into the same medium, and certain amount of energy will absorbed by the medium. So three things will happen when an invisible form of light energy will incident on surface of a medium, right? Okay. Here monochromatic, here again I came to the problem. See here, monochromatic light means it is what light which has a single wavelength. Mono means single, chromo means color, right? So monochromatic light of wavelength, it is what 589 nanometers. Nano means 10 to the power of minus 9. Is incident from air on a water surface, from air onto a water surface, right? Full stop. What are the wavelength, frequency and speed of reflected and refracted lights? Okay. Here wavelength means distance between two consecutive crest or trough. Okay. And frequency means, right, so number of waves produced, that is what number of waves present, or number of waves per cycle, that is what number of waves in 1 second, that is what frequency, right? So we are writing that is what cycles per second. So number of waves produced or developed in 1 second, or the number of waves are propagated, right? So when there is a wave train, one crest and one trough constitute one wave, that is what, okay? So how many like this are present, or how many like this are propagating in 1 second, that is the count to know the frequency, right? Next speed, right? So speed is what, the formula V is equal to n lambda. So V is the speed of light, that is what speed, and n is the frequency, and lambda is the wavelength, right? That is what about wavelength, frequency and speed. But in case of two things we have to find, that is what in case of reflected light and in case of refracted light also, right? Okay. And additionally they have given refractive index of water is 1.33. This value you know very well, but again they have given, right? So constant values will be given. Even in public exam also there is one rule, that is what constant values has to be given. You need not remember, right? But some of the noted things, that is what air, water, because usually every day life, that is what we are in contact with air and water. That's why generally we know what is the refractive index of air and what is the refractive index of water, what is the refractive index of glass, like that. Okay, right. So now we are going to see the solution. First we will go to the reflected light and then we will go to the refracted light. Okay, see this. For reflected light, okay ma, since speed of light in a given medium is fixed and the frequency of light doesn't change when it is reflected from a surface, right? Since the speed of light in a given medium is fixed and the frequency of light does not change when it is reflected from a surface, therefore its wavelength should also remain unchanged. You have to recall one important point here, that is what, when a light is going to reflect, the reflected light has to transmit in the same medium, no? The reflected light has to transmit, has to transport, has to propagate in the same medium. That's why we don't bother about speed because the medium is same. Similarly, frequency depends upon the source of light. Frequency depends upon the source of light. That's why you can say that frequency of light does not change with the medium, right? See, next, when it is reflected from a surface, right? Therefore, its wavelength should also remain unchanged. So, you can write these two statements. That is what speed of reflected light is equal to speed of incident light in air. Speed of reflected light is equal to speed of incident light in air, right? So, what is meant by reflected light? What is meant by reflection, right? So, the light which is sending back into the same medium, the energy which sends back into the same medium, right? So, obviously, reflection means the phenomena due to which or the phenomena in which light bounces back into the same medium. The phenomena in which light bounces back into the same medium is simply said to be reflection. That phenomena is said to be reflection. Okay, right. So that light which is going back to the same medium is simply called as reflected light. Reflected light. Okay. So whether it is incident light, whether it is reflected light, whether it is refracted light, whether it is absorbed light, all the things you have to see like a form of energy, like energy pocket, right? A form of invisible energy, right? So when speed of reflected light is equal to speed of incident light in air, right? The speed is same, no? That is what the c is equal to 3 into 10 to the power of 8 meter per second. And what is the wavelength of reflected light is equal to wavelength of incident light. That is what lambda is equal to 589 nanometers, right? So first he is asking to find wavelength. Wavelength is same. So whatever the wavelength they have given, same wavelength is also for reflected light, right? We need not to calculate. The concept is giving answer. If you understood the concept is giving answer, right? No need of calculation. Next, frequency. Formula C is equal to n lambda or nu lambda, we don't know. So nu is the frequency. Nu is equal to C by lambda. Nu is equal to C by lambda, right? It is what 3 into 10 to the power of 8 divided by 589. Nanometers they have given, ma. We have to convert into meters because this value is in meter per second. So this also should be taken in meter. That is what here meter means meter will get cancelled. Then finally cycles per second or waves per second, that is what 5.09 into 10 to the power of 14 hertz. 5.09 into 10 to the power of 14 hertz is the frequency of reflected light. Next, for refracted light, frequency nu remains constant. This point we already know, right? Even when we were in a discussion about the refraction, there itself I concluded many times. When light propagates from one optical medium to another optical medium, right, it bends at the point of separation of both the media. This phenomena is called as refraction. So when in case of refracted light, the frequency remains constant. You can also say that frequency remains unchanged. Frequency remains unchanged, right? So here constant means it is constant only this particular situation, right? So not if you change the source of light, frequency will change. But whatever the source of light here in case of reflected light you consider, there only we are talking about refraction also. So in case of refracted light, right? So frequency nu remains constant. Both wavelength and speed get changed. Both wavelength and speed get changed. Okay, right. Now see here, speed of light in water. Speed of light in water, VW, that is what speed in water is equal to C by mu, right? This is what here we have to discuss about. That is what relative refractive index. This is what refractive index, okay? And what is relative refractive index and what is absolute refractive index, right? So relative refractive index means speed of light in one medium to the speed of light in another medium. So relative refractive index is the ratio of speed of light in one medium to the speed of light in another medium. That is what relative refractive index. Here speed of light in water is equal to C by mu, that is equal to 3 into 10 to the power of 8 divided by 1.5. So it is equal to 2.26 into 10 to the power of 8. So if you do this calculation, you will get it as 2.26 into 10 to the power of 8 meter per second. It is the speed of light in water. Speed of light in water. You know, refracted light is present in water, no, because it has to travel from air to water, because it is going to refract, right? So that's why speed of light in water is equal to 2.26 into 10 to the power of 8 meter per second, and frequency unchanged. So whatever the frequency we have here, that is the same here also. And next we have to find wavelength. So frequency okay, and speed is also okay, and I mean we calculated. So here it is what wavelength. Wavelength of light in water lambda w is equal to Vw by nu. So it is what velocity of, that is what speed of light in water. Here 2.26 into 10 to the power of 8 divided by 5.09 into 10 to the power of 14. 5.09 into 10 to the power of 14. The mathematical process, the mathematical calculation will give us 444, right? 444 into 10 to the power of minus 9 meters. So you know 10 to the power of minus 9 is nano, no? So you can write it as 444 nanometers, right? Okay. So first problem we completed, ma. Now we are going to see the second problem. What is the shape of the wavefront in each of the following cases, right? So very good question. Here this is important for us. This question makes us conceptually stronger, right? What is the shape of the wavefront in each of the following cases? So the first case is light diverging from a point source. Second, I mean B, A, B, C, right? A is light diverging from a point source, and B is light emerging out of a convex lens when a point is placed at its focus. Listen carefully, and try to imagine the situation. Light emerging out of a convex lens when a point source is placed at its focus. When a point source is placed at its focus, right? Next, C is the portion of the wavefront. The portion of the wavefront of light. The portion of the wavefront of light from a distant star intercepted by the earth. From a distant star intercepted by the earth, right? The portion of the wavefront of light from a distant star intercepted by the earth. So in these three cases we have to find shape of wavefront. Shape of wavefront, right? Shape of wavefront. See here. So now we are going to see the solution. Okay. So if you observe carefully here, it is what in case of light diverging from a point source. In case of light diverging from a point source, the shape of the wavefront is spherical wavefront. Spherical wavefront. What is the reason? The reason is all such points which are equidistant from the point source will lie on a sphere. I will repeat once again. The reason for having a spherical shape when light diverging from a point source is all such points which are equidistant from the point source, will lie on a sphere. Right? Next, light emerging out of a convex lens when a point source is placed at its focus. Right? Here it is what plane wavefront, because the light emerges from the convex lens as a parallel beam for which the wavefront is a plane. You know, when you see the ray diagram of convex lens, right? So there before incident on the convex lens, the rays parallel to the principal axis means after completion of the refraction, the rays will meet at a point, that is what focus, right? Suppose if the rays are coming from focus means after completion of refraction, right? So these are going to meet at a point, suppose if they are coming from focus means after completion of refraction, these rays will become parallel to the principal axis, right? So here it is what plane wavefront, because the light emerges from the convex lens, as a parallel beam for which the wavefront is a plane, right? Okay. Next, C. That is what portion of the wavefront of light from a distant star, portion of the wavefront of light from a distant star intercepted by the earth. Okay. So here also the shape of the wavefront is plane, because a small portion of a spherical wavefront of very large radius is nearly planar. He is talking about the assumption and consideration and the possibilities, right? So you keep in mind, here the shape is plane wavefront, no doubt, but he is giving the reason. That is what a small portion of a spherical wavefront, very large radius, very large radius is nearly planar, right? That is what he is saying, right? Next, we are going to see third problem, right? See here, it is what third problem. Here, it is what, see the third problem, the refractive index of glass is 1.5. What is the speed of light in glass? Speed of light in vacuum is 3 into 10 to the power of 8 meters per second, right? Here in this problem, there are two things, one is A and another one is B. In A, they have given refractive index of glass. He is asking what is the speed of light in glass? So they have given speed of light in vacuum, it is 3 into 10 to the power of 8 meters per second. 3 into 10 to the power of 8 meters per second, okay, right. Similarly, next, B also is there. Here, is the speed of light in glass independent of the color of light? If not, which of the two colors, that is what red and violet, travels slower in a glass prism, right? Suppose if yes or no, first you have to say, then you have to give the reason, right? So first we are going to discuss A. So in case of A, they have given refractive index of glass as 1.5, and what is the speed of light in glass? That is 3 into 10 to the power of 8 meters per second. 3 into 10 to the power of 8 meters per second, right? You know this formula, mu is equal to C by V. That is what speed of light in vacuum by speed of light in medium. It is what absolute refractive index, right? It is speed of light in water divided by speed of light in vacuum, okay? So if you observe carefully here, speed of light in glass, V is equal to C by mu, that is equal to 3 into 10 to the power of 8 divided by 1.5, that is equal to, mathematical process will give us 2 into 10 to the power of 8 meter per second. Now B, in case of B, is the speed of light in glass independent of the color of light? If not, which of the two colors, red and violet, travels slower in a glass prism, right? See here, so it is not possible. That is what answer is no. Speed of light is not independent of the color of the light. So the violet color travels slower than the red light in a glass prism. This is because refractive index for violet is greater than the refractive index of red. Mu V is greater than mu R, and V is equal to C by mu. V is equal to C by mu, where speed of light c is the speed of light, and mu is the refractive index. Mu is the refractive index. Okay, right. So in this class, if you focus on these three problems, so see here, in case of first problem, he is asking to find wavelength, frequency and speed of light in case of reflected light and refracted light. Okay, so we did, and one important that is what correction here, in case of a refracted light, I told you this is what relative refractive index, no, right? But it is not relative refractive index, no, it is what absolute refractive index, because here he is talking about speed, no, that's why, right? If you think and if you do that by using relative refractive index also, we may solve, but here we are using speed of light in water, means it is absolute refractive index, right, not relative refractive index, right. Next, in the second case, he is asking the shape of the wavefront, right. So in different situations that we discussed, and in case of third problem, in first he is asking the speed of light in glass, and second he is asking the relation between, that is what color of light and speed of light, color of light and speed of light. Okay, right. Thank you. We will continue in the next class.